Code concepts, logics, that's a kind of weird word. What I mean is these are capabilities that we make use of all the time that are built into PFC and are part of the way that we go about interacting with the model. So we've covered the graphical user interface, with the most important part there being the plotting. That's how we're going to visualize things. Documentation, very extensive. If you're going to be working with PFC as you are, it would be worth your time to go through that documentation, look at some of those examples. You'll gain a lot of information. You'll learn a lot if you go through that stuff. So we're going to talk about the command processor and some of these other things. We're going to hit them one by one and do examples as we go. Okay. So again, I call this the command genie, right? It's very powerful. You can give all kinds of sort of free format, right? So it's a ball attribute radius. It's expecting a floating point number. It can just be an integer. It's smart enough to convert it, right? Here it's expecting a two-dimensional vector, two floating point numbers, right? I can specify them. I can put commas in there. I can put in brackets. I can not put the commas. I can just give the numbers. All of those are fine. This in the example is there's a fish variable called myval. And so I can just, if you're going to give it to a command, you got to use the braces. And basically it says evaluate this, which is a vector, and feed it into this command. Okay. As we've mentioned before, these commands are associated with the different components. So all the commands pretty much, they're going to be ball create or wall create, things like that. You can type a question mark. So you could type the word, you can start typing in a command, ball attribute velocity question mark, and then it's going to say, oh, here's the things that I'm looking for. Add the next token in this command. That's a quite useful thing. Okay. I'm going to just fire this thing up, logics overview, just to give an example of that. So here we go, right? Ball create question mark. Ball create. Well, the ball create command, it's expecting one of these different things, right? It's this ball create. And if I look at the F1, right, notice it's expecting a group, an ID, position. Those are the next keywords, right? So this is sometimes helpful, right? I can say ball create question mark, and then it'll tell me those are the things that it's expecting in the command. Okay. Get rid of that when we're ready to look at that. We've already done this, right? You can highlight the command and hit F1, brings up the manual page, right? Wall generate, boom, there's the wall generate command, okay? Now, history logic. This is a way that we can monitor the response of the model as we're moving along in the simulation. And so basically we tell PFC, I want you to sample a certain value, and I want you to, as you're sampling it, you're going to internally store all that information, and then I can go and I can use a special plot item called the history plot item to plot that on the screen as things are going on or after it's done. I can also dump this out to a text file, right? So you might say, I want to create a ball history of the displacements of ball number 26 and just keep monitoring that. And then we can plot it. So here's my example, okay? And we're gonna look at this, but first let's so yeah, we're gonna do this step by step, but the basic idea is we're gonna make a collection of particles. We're gonna let them settle under gravity. Then we're gonna make a wall on the top here, and we're gonna slowly push it down, okay? And what we're gonna do is monitor a history of the total force acting on this wall in the Y direction. And so then we're going to make a history of that, and we're going to plot, I'll call it flattened force versus, and I'm also going to monitor the displacement of this wall in the Y direction. And so we can then plot, we're going to plot the force versus the displacement, and then we're going to run the model. And as we're pushing down, we're going to see, in this case, the force and displacement are going to go up like this, right? As I continue to push this thing down. That's what we're going to try to do. Okay, so let's open this thing up. Let me start again from scratch. In the Logix overview, there's a project. So I'm going to open it up. Let's just first run it. This is, I call it master.dat. This is going to call in a data file and execute it. Then it's going to call in another data file and execute it. But we're going to just do that first data file first. It's called my first pack. And this is essentially the same thing. This is exactly the same thing that we did before. So I'm just going to run this thing. And hold on, I can't see the top of my screen. There we go. I'm going to run this thing and I'm going to look at system view, and there's my packed system. That's the same thing we did before. Okay. But then I've got this new one here, compress me. So notice in the first data file at the end of it, we did a model save and we called it tight pack. So now in this one, which is called compress me, I'm going to restore that model and then I'm going to operate on it. Okay. So I'm going to give it a new title, sand pile of balls in a box with gravity loading. That's the initial state. And so what am I going to do here? I'm going to give the ball delete command because I'm going to delete the particles at the top. So before I do that, let's do a pause to see what's happening. So I run this up to here. It just changed the title. Okay. Notice the title is appearing at the top of the plot. Okay, so this is that initial system. Now I'm going to delete the balls near the top. So I'm just going to say continue. Boom, there we go. Deleted the balls near the top. Then I'm going to go and turn on gravity and cycle till I get to equilibrium. So let's take out the return. Put a return here. So let's run this and watch what it does. Continue. So delete the top and then cycle to equilibrium. See it pushed up. It's in equilibrium. I just want a system now that I can push down on. So this was a quick way to get it. Okay. So there's my system. Now I want to push down on it. So here, now we're going to give a new title, push down on the sand pile, record platen, force displacement. So first of all, I'm going to give a sign of velocity to the top wall. So how do I do that? With this command, wall attribute velocity in the Y, there's a number, meters per second. And then this is basically saying which facet of the wall. And if I look at my system, when I generated it, if I say wall, facet, color by name, there we go. There's 4 facets and they've been, because I did the wall create command, it automatically gave them names, bottom, left, right, and top. So the red one is the top. That's the wall that I want to give it a velocity. So that's what this range set name is doing. Okay, and we'll talk more about the range logic a little bit later. So this is identifying the top wall and assigning it a velocity. Okay, so it's just going to move like that. So then we're going to cycle 2000 and watch that thing go down. But before we cycle, we're going to, we're going to move it down fast and then we're going to move it down slow. Okay, so that we can just make this thing go fast. Okay. And say, let's do return. So if we run this thing up to this point, we let it go up. And now after it gets to equilibrium, we're going to move that wall. Watch this top wall. We're going to move it fast. There we go. And now when it gets close, we're going to move it slow. Okay, and now we're going to watch. So now if I just cycle, it's going to start pushing down on that system, right? Okay, because it's all set. I'm giving it a velocity. It's just going to keep moving at that velocity no matter what happens. It doesn't care what the force that builds up is. Okay. But now I want to monitor these histories. So first of all, I'm going to reset the displacement to 0. What does that mean now? PFC associates a displacement vector with every wall and with every particle. This displacement vector constantly gets updated every cycle based on the amount of displacement that just occurred, and it keeps getting summed up, okay? The only reason it's being used is it's being used for monitoring things, okay, and used for visualization. So what I'm doing here is I already pushed that wall down quite a bit, but I don't care about that. I only want to start monitoring the displacement given this reference state of 0. So starting at this point now, where the wall is, at this point, it's just a little bit above the, that's not there. It's a little bit above the system. And now I want to take a history. So one of the histories in this line is wall history name. I'm going to make a history of the Y displacement of the top wall, and then I'm going to give the history itself a name. So this is a history called delta, and then I'm going to make another history called force, which is force contact Y. So there should be a wall history command. So wall history force contact Y. There we go, the Y component of the contact force, and then there's other information that you have to give. Basically, you got to tell it which wall, okay? And you can give a name to the histories. So let's run to this and look at the system. And I'm just going to run the whole thing because it runs fast right from the, I'm going to run it from the beginning. So let them go up, move that wall into position. Here we go. And I haven't done any cycles yet, but I gave those history commands. So I can, for example, say history list. There's my list of all the histories that are being monitored currently. There's the names of the histories, force, delta, and here's what it is, the Y contact force of wall 3. Okay. Now I'm going to cycle. I'm going to continue. Okay. And so now we want to actually plot those histories. We're going to go here. We're going to say plus, I want to add a new plot item. And here it's called a history chart over here. So I double click history chart. Now it says, what are the histories that exist? The force and the delta. So I want to plot the force, and let's turn off the balls, turn off the axes, turn off the force chains, turn off the walls. There, that's my history. Okay. And so it's just right now the force. See, the force is increasing, the Y force on the wall. But I can say I want to plot it versus something else. So by default, it plots it versus step number. Okay. So we started at about 6,800, and now we've taken some more steps. We're up to like, here we go, step number 9246. So that's what it's plotting it against, right? Started out as 0 because it wasn't quite touching, and now it's building up, which makes sense. But I want to plot it versus delta. So it says verse here, and the name is delta. Boom. Now it's plotting the Y force versus delta, but delta is the Y displacement of the wall, which is negative. So it's 0 and it's going negative here. So I can reverse that. So I want to flip the axis of the X axis, so I can say reverse. And it's telling me up here, it's telling me history of force of Y contact of wall 3 versus the reversed Y displacement. And of course I can label these axes, right? So I'm going to say platen displacement meters. There we go, platen displacement. And then I'm going to do the Y axis, and I'm going to label that one platen force in newtons. And so notice here's the history, and I can always change colors of these. Where the heck is the color? Oh, right here for the force. There's my color. Draw it as a line, red. I could also draw it as marks. There's all the sample points, right? But I want to draw it as a line. There we go. Red, I can change, of course, the thickness of the line, all that kind of stuff that you would expect. I'm also, as you're going to be able to see, you're going to be able to plot multiple things versus something, a single thing on the x-axis, right? So we might have force in the x and force in the y. We might be doing a biaxial test, and we're going to be plotting axial stress, and we're also going to be plotting confining stress at the same time versus platen displacement, right? Things like that, okay? And notice it's just a plot item. So it's just in the list of plot items. So I can turn on the balls, for example, and I can overlay this on top of itself. And so that's what I did in here, right? I'm plotting the walls. If you look in the legend, I'm plotting the walls and I'm plotting the history, that particular history, right? Force and displacement. Okay, makes sense? That's a history logic. Use it all the time.
Yeah.
Excellent. There's also what we call table logic. This is basically you can give it a set of XY pairs, and then if you want, you can query that. So, you know, for a given X value, it's going to interpolate to find the Y value. This can be plotted with the table plot item. So here, for example, in FLAC 3D, we have an analytical solution of deflection versus Y distance across a shell. And so we build up a table of the analytical solution with a whole bunch of data points, which we're going to draw as a line in black. And then we're going to sample the results from the model at a selected number of points. And we're going to add those as a different, as another table. And then we're going to draw those as dots, as crosses. And then we're going to plot these two tables on top of each other, right? And so, you know, you get the idea. So this is often useful if you're, you can manipulate a lot of data if you want. You can take a history, for example, and dump it into a table. And then you can, for example, make queries on it, you know, and interpolate between things, for example, or do things like this, okay? That's the table logic. Now the range logic, this is super used all the time. So we have commands. So a typical command is ball delete. Now, if we do not give a range, that command will apply to every single ball in the model, okay? So if we don't give a range, it applies to everything. If we give a range is like a filter. And so it's only going to apply, that command will only occur for this subset of particles of whatever the range is. So there are these things called range objects. So what this is, this says, what's the range? Well, any ball whose position lies between X min and X max. Only delete the guys there. So for example, here's my initial packed system. And here's the global coordinate 0, 0, 2, 2, because I made a box. This is the same example we've been working with. We made a box that went from 0, 2 in the X to 0, 2 in the Y. So that's our packing. And now we give this command, ball delete position X 0.5 to 1, and there we go. So a command only applied to that chunk. So this was a data file called rangeIt. And so there we go, return. So to illustrate this again, notice I'm going to restore that tight pack system, change the title, and do the ball delete. So let's see what happens. Boom, system view. There we go. Let's turn off the histories and then turn on the axes. Now notice something about the axes plot item. There's a little thing called fixed here. If I click fixed, what that does is it always fixes the axes system to the lower left corner of the view. If I do not check fixed, it puts it at the 0, 0 point of the coordinate system. Okay, sometimes you want that, sometimes you don't. So I'll put it over on there on the corner. Okay, so there's the first simple idea, ball delete position X. Okay, there are many different what we call range elements, position, circle, annulus. So here, for example, is using the circle range element, right? So if we say delete everybody that's in a circle with a given radius and center, there we go. Radius is 0.5, center 1.2x, 1y, right? Delete all the balls whose centroids lie in that thing. So that's a different that's a different range element, right? So again, I'll just run this thing. Notice I'm going to do a restore. So I don't care what it does there. I'll let it do it. But now I'm going to restore the tight pack again. This time I'm going to delete it in a circle. So if I run that, there we go. Deleted it in a circle. Notice there's walls in here and everything. I can continue to cycle. I can cycle now. And so it should just move in, and now they're just floating around because they're not packed. Okay. Going back to this, these range elements can be combined with Boolean logic. So I can say, I'm defining a range of balls who have position between 0.5 and 1, and also lie within the circle. So there we go. A union, position right here, circle right there. I did a union. So that's the range element, right? I can also do the inverse of this. So I can say position everybody that's not between 0.5 and 1, and then also everybody that's not part of the circle. And so there's the intersection of those two, not the intersection, it's the union of those two things. So the range logic is very powerful, and we use it all the time to basically do operations on restricted groups, not groups, restricted objects. Think of it as a filter. Okay. Now we have this idea of a grouping. Okay. We can take model objects and we can assign them to different groups. Okay. And so think of it like this. Every group has a name. Okay. So I'm going to create a group called left side. Okay. And this is a ball group command. So it's a command like any other command. So this is going to use the range logic, right? So this is going to, just the guys who are between 0.5 and 1 are going to become part of a group. They're going to get a label called left side. So think of it like this. Here's every ball has a big chunk of data. Remember when we clicked on the ball, it showed that big box in the middle with all the different data. So, for example, each ball has a radius field. It has a density field. It also has a bunch of these group names that are associated with it. Okay. So notice after this command, the balls that are assigned to it are going to have this left side. Think of this like a sticky note that we take on those balls and we stick this word left side on them. So if we do that command, ball group left side, okay, notice we can then say use the ball plot item. So the shape is a ball, so they're going to get drawn as these discs. The shape is not an arrow or anything. Shape is a ball. And now we're going to color it by a text value. And one of the text values we can color it by is called group. So, look at this. The red ones have the word left side written in their default group slot, and the other ones have none. They don't have anything. Okay, makes sense? So that's a group called left side. Now, you can have, their balls can be part of more than one group. You can have multiple sticky notes on a given ball. It might be part of, so for example, and these are, we call these things slots. So we might have a ball that's part of the word, so these slots can be named. So we can make a slot called the layer, and we can make a slot called the material. And then we can give it a name. So we say, what layer are you in? You're in the deep layer. What material are you? You're clay. So this is the command that does that. So in the slot layer, I want to put the word deep, and I only want to do it for the balls that have Y position from here to here. And then I want to do this for the other guys. So here's what that would look like. So notice deep in the slot layer, position Y, 0 to 0.3, 0 to 0.3, ball plot item, deep or none, because I'm in the ball plot item now. I'm doing text value group, but which slot do I want to see? I want to see the slot called layer. And so just for these guys, they actually have a slot called layer, and they have the word deep associated with them. Now the other guys, the second command, put a slot called material in there, and they put the word clay. And so those were these guys. So in the slot material, that's all we're looking at is the slot material. So these guys don't have a slot material, but these guys do. Now, some of the balls, namely the guys over here, have two labels connected with them. And now we're going to see that. So now I want to look at any slot. So all of the slots are going to be shown. So notice these guys are just part of the deep, but these guys are part of the deep and part of the clay, right? And so there it is. They're part of deep and they're part of clay. So this is the range logic. This is also used all over the place in PFC, you know. So again, you got, you make a big system like a sandbox model, right? And then you have different layers in there. So you can basically you can make a slot called layer, and you could put whatever you want, clay, granite, whatever, stuff like that. Okay, so that's an example of the group logic. Now, there's also something called measurement logic. Now in PFC, as you know, it's a discrete system. So we have these particles. There are certain things you can measure within certain parts of the model. So you define what we call a measurement region, which is either a circle or a sphere in 2D or 3D. And these are the different things that you can measure with that. So particle size distribution, coordination number, which is average number of active contacts per particle, right? Porosity, what's the porosity in that spherical region? And then you can also measure the equivalent stress tensor that corresponds to that set of force chains in that volume. You can do some fancy mathematics on those force chains, and you can turn that into an equivalent stress tensor within that region, okay? The other thing you can do is you can ask for the strain rate tensor. So from your continuum mechanics, we talk about strain, right? So strain is, like strain in the x is partial derivative of u over partial derivative of x, right? du dx. So what the strain is the spatial variation of the displacement field. That's what a strain is. In the world of PFC, we don't have displacements. We just have velocities that we always know. We know the velocities. We know the field of velocities. So what we can do is we can do a velocity gradient tensor, okay, by basically doing a best fit to the velocity field that we're sampling. And if we take that strain rate tensor, which we get from the measurement logic, and if we keep on multiplying it by the time step delta t and summing, what we actually get then is the strain, the thing that we're used to, the continuum quantity called strain. And so we're going to use this logic, for example, if we want to do a triaxial test. We're going to put a measurement region inside the middle of our sample, and we're going to keep asking it for the stress. And then we're going to also have a little fish function that keeps asking it for the strain rate tensor and keeps multiplying and summing up, and we're going to get a strain. And we're going to see that these measures are pretty good. These are like averaged in quantities of these force chains and of these velocity fields. And so the idea here is this one in that example, that hacked system we have, we can say create a measurement region. Every measurement region has its own unique ID. So this is going to be measurement region 10. And now we have to, it's a circle, so we got to give it a radius and a position, right? So this is where that region is going to be. And then we can say measure list. So this is going to list out all the measurement regions that we currently have, and it's going to give me this different information about it. So here we go. What is the porosity that it's computed? 0.112. Coordination number 4.3. Average number of contacts per disk. And then here's the stress tensor. sigma x, sigma xy, sigma yx, sigma yy. When you compute stress this way, you are not guaranteed to have a symmetric stress tensor. It will be close to being symmetric. And again, we'll look at this. We're going to squeeze this, and suddenly we're going to see, oh, the stress in the y is compressive, and it's really big compared to the stress in the x, etc. Okay, so that's an example of the measurement logic. The last thing I want to discuss is you can associate information or data with every object as much as you want. Okay. Think of this as, we call these extra variables. So this is extra information that you're assigning. Okay. This is very general type of data. This can be floating point number. This could be a string like I am Fred. This could also be a vector quantity. Okay. So let's say you knew a magnetic field variation over some region of space and you pack it with particles. You could go and assign the magnetic dipole as a vector at every single particle location, and assign it to every ball. And then you can plot these things. Okay. So here's an example. So this command at the top is going to the balls that are within this range, okay? And what's it doing? It's creating an extra variable, and these extra variables are again in slots from 1 to 128. So in slot 1, there's going to be an extra variable, and we're going to assign it a vector 1 1, and we're doing it to every single ball in that range. Then we can use the plot item. So again, the ball plot item, but this time the shape is an arrow, and we're coloring it by a vector quantity. What vector quantity? Oh, the extra vector quantity. What slot or what index? 1. And so here we go. There's drawing it as arrows. Remember, we assigned 1 1, but of course it could have been anything. For each one could have been different, right? And here it's showing me drawing the arrows. Okay. So this is again a very powerful generalized logic. If you may recall from the first day's lecture, when we did the rock cutting, and we did the rock cutting on the system that had applied pressure on the surface for the effect of the drilling mud, we were constructing a chain of particles, and once we had the chain of surface particles, we were able to apply an external force based on the pressure and the orientation of the chain locally for that ball. And then there was a plot, and it showed little arrows that were in the direction of each one. And let me just, I think it's in here, just to make this clear. Sorry about this. Let's see, catch up. Where is that chain? Am I showing it here? Don't think there it is. So in this plot, see these little red guys? This is the applied force on each particle. And so this applied force was stored as an extra variable for each particle. And then using the ball plot item and using the arrow business, I was able to then make the plot that you saw. Okay. So this is the idea of extra. So I'm assigning here in extra slot 1, this vector 1 1. Here, I'm assigning a string called cement to guys in a different range, right? So I can now plot color by text value extra slot 2. And so there we go. The other guys, the yellow ones, don't have an extra slot 2, but the guys who do, there we go. And the only thing I assigned was cement to all of them. So it's going to say cement, but I could have had different names here, right? So there we go. Extra logic. You can put this, you can assign data to the object. There's extra fields for contacts as well. You might have certain contacts that you want to name in a certain way. Maybe you have different types of local cementation, and then you want to name them, alpha cement and beta cement. And so then you could assign those strings to the extra values where the contacts, and then you could plot those and see, oh, there's that type of cement, there's the other type of cement. Okay.